You know, usually when we look at like massive machinery, a towering offshore oil rig, or a submarine plunging into the icy depths, or even just a gigantic industrial crane over a city skyline, our eyes are naturally drawn to the steel.
Oh, absolutely.
Right. We see these colossal beams, the giant thick bolts, the heavy metal gears, and we just sort of assume that raw size and strength are what hold everything together. We trust the visible bulk of the materials.
Yeah, and I mean, it's a massive blind spot in how we view engineering, honestly. We look at a steel bridge or a drilling rig and assume its survival is purely a matter of metallurgy and mass.
But what if I told you that all that steel, all that raw, visible power, would essentially tear itself apart in a matter of hours if it weren't for an invisible layer of chemistry sitting right between the metal parts?
A layer that's, what, just fractions of a millimeter thick?
Exactly. Welcome to the deep dive. Today we have a fascinating mission for you. I have a source right here in front of me, and it's not some, glossy textbook or marketing brochure. It's a highly dense, single-page technical data sheet for a product called Jet-Lube MP-50 Moly paste.
Right, the MP-50.
Yeah, and our goal today is to decode this heavily technical document to uncover the extreme service chemistry that actually keeps the world's most highly pressurized machinery from destroying itself.
And this document, I mean, while incredibly brief, it's just packed with the kind of physical extremes that most materials simply cannot survive. It really highlights how the most critical components of modern infrastructure are often the ones you never actually see.
Okay, let's unpack this, because we are going on a journey from the microscopic friction of metal surfaces all the way to deep-sea operations.
Sounds good.
Before we can talk about how this stuff is saving military hardware, we need to establish what it physically is. So, looking at the specs on this sheet, what exactly is MP-50?
Visually, the document describes it as a thick, non-melting paste, ranging in color from blue to black.
Kind of like a blue-black armor.
Right, exactly.
Mm-hmm.
But the physical capabilities come entirely from its specific blend of ingredients. It contains a very high percentage of a solid, low-friction compound called molybdenum disulfide.
Which is usually abbreviated as MOS2, right?
Yeah, MO2. And that solid is suspended in a petroleum fluid, and then the whole mixture is held together by an organo clay thickener.
Okay, so it's essentially this dark paste loaded with MOS2. The organo clay thickener stands out to me, though.
How so?
Well, most everyday greases you might use in your garage are thickened with different types of metallic soaps. But the sheet specifically points out this clay thickener gives it a non-melting consistency, meaning it stays exactly where you put it, even when things get incredibly hot.
Yeah, it doesn't run or drip.
Right. And applying it with a brush or spatula, it's sort of like frosting a cake. But, a cake that needs to survive extreme weather, live steam, and corrosive acids.
That is a very intense cake.
Seriously. And speaking of hot, the temperature ranges listed here are just staggering.
They really are. For standard anti-seize applications, the manufacturer rates it to operate from negative 300 degrees Fahrenheit, which is about negative 185 degrees Celsius, all the way up to 750 degrees Fahrenheit, or 400 degrees Celsius.
Okay, negative 300 degrees is colder than any natural temperature ever recorded on Earth.
Yeah, it's extreme.
And 750 degrees is basically the temperature of a roaring wood fire. But the sheet actually pushes it even further than that, right?
It does. It states that if this paste is used in mechanical components that are not exposed to the open air, you can anticipate good lubrication results up to 2,000 degrees Fahrenheit.
That is almost 1,100 degrees Celsius.
It is an astonishing thermal envelope. You have a single compound surviving conditions that would literally turn most conventional materials to ash, or just, shatter them like glass.
Wait, hang on. I'm looking at these ingredients again. It's got a petroleum fluid base acting as the carrier, right? If you are exposing petroleum to 2,000 degrees Fahrenheit, shouldn't that liquid base just instantly vaporize into smoke? How is there anything left to actually lubricate the metal parts if the grease itself burns away?
What's fascinating here is that the petroleum grease vehicle absolutely does fail under those extreme conditions.
It does.
Yeah. It can vaporize under that intense heat, or it can be physically squeezed out of the machinery by immense crushing pressure. But that failure is anticipated.
Oh, so it's designed to do that.
Exactly. It's actually a built-in, fail-safe mechanism designed around that primary ingredient we talked about, the molybdenum disulfide.
The MOS2.
Yes. The document notes that MOS2 is nearly inert in operating conditions up to 600 degrees Fahrenheit, and it can survive much higher without oxygen.
Okay, so it just stays there.
Right. So if the extreme heat or the insane mechanical loads squeeze out the petroleum carrier, which would normally leave bare metal rubbing against bare metal, The solid Moly disulfide doesn't leave.
Yeah.
It stays behind, physically bonded to the metal to protect the working surfaces.
Okay, so the petroleum liquid is really just the delivery mechanism.
Precisely.
It transports the MOS2 to where it needs to be. And then, once the environment gets too hostile, the liquid might bail, but the MS2 stays and does the heavy lifting.
That's a great way to put it.
The datasheet uses a very specific engineering term for this, actually. Boundary lubrication.
Boundary lubrication is a foundational concept if you want to understand heavy machinery.
How does it work, exactly?
Well, think about when you drive your car down the highway on a rainy day. Your tires can sometimes ride up on a thick layer of water, right? They lose contact with the road.
Yeah, hydroplaning, it's terrifying.
Right. In engineering, that's called hydrodynamic lubrication. The two moving metal parts are floating on a thick layer of oil. But under extreme service like the slow, heavy movement of a massive industrial crane, that thick fluid layer gets completely crushed and pushed out.
So you punch right through the water layer and hit the asphalt, basically. You are down to the very boundary of the metal surfaces.
And this is where the physics get really dangerous. Because if you were to take a seemingly perfectly smooth machined steel bolt and put it under an electron microscope, it wouldn't look smooth at all.
What would it look like?
It would look like a jagged, rocky mountain range full of steep peaks and deep valleys. Engineers call those microscopic peaks asperities.
Asperities, okay. So if you rub two of those microscopic mountain ranges together under thousands of pounds of pressure, those peaks are going to violently collide.
They do more than just collide, actually. Under extreme pressure, when two bare metal peaks scrape together, the friction generates so much localized heat that they actually cold weld.
Wait, they weld together?
Yeah, they briefly fuse into a single piece of metal and then instantly tear themselves apart as the machine continues to move.
Oh, wow. Galling, seizure, slip. The sheet lists all of these as things the paste prevents. And when you understand that microscopic mountain range, those terms stop sounding like, minor mechanical hiccups. That is literally the sound of thousands of pounds of metal physically welding together and ripping itself apart in real time.
Which is why the MP-50 acts like a microscopic paving crew. The text explicitly says it plates the metal surfaces.
Plating it.
Right. It packs the -2 into those deep microscopic valleys and levels out the high peaks. You're essentially transforming a jagged mountain range into a smooth, low-friction plateau of solid lubricant.
And by doing that, you increase the actual load-carrying area.
Exactly, yeah.
The crushing force isn't just focused on a few fragile microscopic metal peaks anymore. It's distributed evenly across the smooth MOS2 asphalt.
That's right.
And this makes sense of a detail the sheet emphasizes, too. It's tenacity. It says it adheres tenaciously to metal surfaces. I mean, if you're building an armored shield at the microscopic level, you need it to stay exactly where you paved it, even when applied directly to hot surfaces.
A seizure or a heat freeze out in the field isn't something you can just, buff out. The machinery locks itself together permanently.
That sounds like a nightmare.
It is.
Yeah.
If that happens on a critical piece of infrastructure, the entire operation just grinds to a halt.
Well, let's follow that thought to the actual environments where this level of protection is required, because you don't buy a tub of high-tech paste with a 2,000-degree tolerance to fix a squeaky door hinge in your kitchen.
No, definitely not.
The datasheet specifically calls this an extreme service lubricant, and the examples they provide are heavy-duty industrial and maritime environments.
The applications are where you really see the stakes involved here.
Right. It mentions subsea risers. Those are the massive, thick-walled pipes that connect a seafloor oil well to a surface facility, constantly enduring freezing ocean currents and immense internal pressure.
Right.
It also mentions blowout preventers, or BOPs. For anyone listening, a BOP is the giant, highly complex valve system on an oil rig. It is the ultimate fail-safe designed to shear off pipes and seal a well to prevent an uncontrolled gusher.
A very critical piece of equipment.
Absolutely. It also lists highly loaded gears, open spur gears, and marine transmission gears. The sheet actually advises that any application prone to scoring should be pre-pressed with MP-50 before it even goes into initial service.
That pre-pressing directive is crucial. You don't wait for the machine to start grinding to apply the lubricant.
Right. You want it there from the beginning.
Exactly. You embed this boundary lubrication right from the start. You pave those microscopic valleys before the metal peaks ever have a chance to touch, ensuring the integrity of the gears from rotation number 1.
That makes total sense.
But to truly grasp the level of trust engineers place in this chemistry, You have to look at the military specification mentioned in the text.
Oh, the Navy CA spec. This jumped right off the page for me.
Yeah, the document states that MP-50 is the only product specified in the Navy CA manual, specifically TMSS 9958 AAMMA 100, Volume 10, Book 1 for Marotta control valves.
The only product. I mean, that is a massive endorsement. For a naval engineering command to single out one specific paste for their control valves, the testing must be absolutely brutal.
The datasheet breaks down exactly why it won that exclusive spot, actually. They ran high-pressure, multiple actuation tests.
Okay, so testing it over and over.
Right. Imagine a control valve on a submarine managing highly pressurized air or hydraulics, rapidly slamming open and closed under immense force. With competing products, the testing showed that the torque required to physically turn or move the valve kept increasing.
So the lesser lubricants were degrading.
Yes.
They were either getting squeezed out entirely or maybe baking into a sticky glue under all that friction.
And when the lubricant degrades, the friction spikes. If the torque required to open a valve increases with every single use, eventually, a human operator or even a mechanical actuator simply won't have the strength to open it.
It becomes a fatal single point of failure.
Exactly. But with MP-50, the testing showed almost no loss in performance. The actuation torque remained consistent cycle after cycle because that solid MOS2 layer refused to yield.
Wow. Here's where it gets really interesting for me, though. We've talked extensively about surviving fire, immense crushing pressure, and deep-sea deployments.
Right.
But the document also explicitly notes that it can be applied at temperatures as low as 0 degrees Fahrenheit or negative 18 Celsius.
Yes, the cold weather application.
And it gives a specific chemical reason for this cold weather performance. It points out the paste utilizes a low pour point oil base. Why does that specific base matter when you compare it to the older technologies the text mentions, like asphaltic or wax-based lubricants?
What comes down to a very practical issue of physical labor in hostile environments.
Huh.
Older industrial lubricants often relied on heavy asphalt or wax to achieve that thick, sticky consistency that prevents them from washing away.
Okay.
But if you take wax and drop the ambient temperature to 0 degrees Fahrenheit, it solidifies.
Right. Think of putting a candle in your freezer. It turns rock solid.
Exactly. If your lubricant freezes solid inside your machinery, the equipment becomes incredibly stiff. The worker trying to turn a bolt or actuate a gear has to exert massive amounts of torque just to overcome the frozen grease.
That sounds exhausting.
It is.
Okay.
So, by utilizing a petroleum oil with a very low pour point, meaning the specific temperature at which the oil physically stops flowing is extremely low combined with that clay thickener, MP-50 maintains its workable consistency.
So it provides reduced torque in the dead of winter.
Yes, allowing workers to operate machinery without fighting the lubricant itself.
And when a worker isn't fighting frozen grease out on a rig in the North Sea at 0 degrees, they work faster.
Much faster.
And out on an offshore rig, speed isn't just about comfort, it's about the staggering economics of downtime. The datasheet is actually remarkably blunt about this. Under the benefits section, it outright admits that MP-50 is expensive when compared to standard mandrel lubricants.
Yeah, if we connect this to the bigger picture, it is incredibly rare to see a technical document so bluntly admit its own high price tag.
Very rare.
But it does so to make a broader economic argument. The upfront cost of a bucket of this paste is a mathematical rounding error compared to the real-world operational savings it secures.
The text outlines exactly where those savings come from, too. You get extended mandrel life, you get better machine surfaces with fewer imperfections, and most crucially, reduced downtime and greater efficiency.
In heavy industry, an hour of downtime on an offshore drilling rig can cost hundreds of thousands of dollars.
Just for 1 hour.
Easily. If a rig has to stop drilling because a massive structural bolt seized up, cold welded itself to the threads and sheared off, that is a logistical nightmare.
Yeah, I can imagine.
The rig sits completely idle, bleeding money, while a crew tries to extract a broken bolt. Paying a premium up front for a blue-black paste that guarantees the bolt can be tightened and loosened safely suddenly looks like the ultimate bargain.
Which brings us perfectly into the physics of how these machines are actually assembled. To ensure that kind of reliability, structural engineers rely on very precise math.
Very precise.
And this single-page datasheet actually provides the specific variables needed for the physics of tightening a bolt. Under product characteristics, there's a stat called the nut factor.
Oh, yes.
It has an asterisk next to it. For MP-50, the nut factor is listed as 0.11 for high chrome alloys at 60,000 psi contact stress.
And at the bottom of the page, it provides the short form equation that utilizes that exact number. T equals K times D times F.
Right. T equals K times D times F, where T is the torque you are applying with your wrench. K is that nut factor, the 0.11. D is the bolt diameter, and F is the bolt tension generated during tightening.
All right.
But there's a fascinating semantic distinction here that I want to highlight. The text specifically warns that K, the nut factor, is, quote, sometimes incorrectly called the friction factor.
Yeah, that's an important note.
Why is it dangerous to just call it a friction factor? I mean, why does a worker tightening a flange on a blowout preventer need to know the difference?
It really highlights the extreme precision required to keep these machines safe. Think about the last time you tightened a bolt on a car tire, or maybe assembling a piece of heavy furniture.
Okay, sure.
You pull on the wrench, applying a twisting force. That twisting force is torque. But the twist isn't what holds the car tire to the axle. What holds it together is tension.
The clamping force.
Yes. As you twist the nut, the threads act like an inclined plane, pulling the bolt and actually stretching it slightly, like a very stiff spring.
Oh, I see.
That stretching creates tension, clamping the pieces together. The problem is that translating twist into clamp is highly inefficient. Roughly 90% of the energy you put into the wrench is consumed just by overcoming friction in the threads.
90%.
Yeah, only about 10% actually goes into stretching the bolt.
So torque is the twist, tension is the clamp, and friction is the massive tax you pay in between.
Precisely. And this is why the nut factor, K, is so critical. It is an empirical multiplier that accounts for everything happening in that joint.
Everything.
Yeah, it accounts for the raw surface friction, yes, but also the thread geometry, the specific alloy of the metal, and the exact performance of the lubricant under 60,000 pounds of pressure.
So if you just call it a friction factor,
Yeah.
you are oversimplifying the physics.
Exactly.
You're ignoring all the other variables at play inside those threads.
And if your calculation is wrong on a high-pressure system, the results are catastrophic.
Yeah.
If you underestimate the lubrication, the bolt might feel incredibly tight to your torque wrench, but you actually spent all your energy just fighting friction.
Wow.
You didn't stretch the bolt enough, the clamping force is too low, and the pressurized pipe leaks or, explodes. Knowing that the K value is a rigorously tested, reliable 0.11 allows engineers to calculate exactly how much torque is required to achieve the perfect, safe clamping force every single time.
So what does this all mean? We started this journey looking at colossal structures, drilling rigs, submarines, massive industrial gears.
Yeah, we did.
And we've drilled all the way down to a dense one-page document detailing a simple blue-black paste. We've learned that it has a dropping point listed simply as none, which frankly feels like an absolute engineering flex.
Oh, totally.
It literally will not melt and drip. We've seen how it uses molybdenum disulfide to pave microscopic valleys in the metal, defying 2,000-degree temperatures and crushing forces to prevent bare metal from welding itself together. And with a friction coefficient of just 0.06, it really is a marvel.
It acts as an unsung microscopic hero of our modern industrial world. The greatest takeaway from this datasheet isn't just the extreme temperature ratings.
Yeah.
No, it's understanding the sheer impact of hidden variables. Things like microscopic asperities, the pour point of a carrier oil in freezing weather, or a mathematically precise nut factor. Mastering these invisible details is the only way we prevent catastrophic macro-scale disasters in the most unforgiving environments on Earth.
Which leaves you with one final thing to ponder long after this deep dive ends. We have clearly mastered the chemistry required to survive 2,000-degree heat and the crushing, freezing depths of the ocean.
We have.
But as we push our engineering ambitions even further, like, say, into the extreme heat of deep geothermal drilling or trying to operate heavy machinery in the wild temperature swings of a Martian colony, will this blue-black paste still be enough?
That is the million-dollar question.
Right. Or are we going to have to invent entirely new states of matter just to keep our future machines from tearing themselves apart? Thanks for joining us on this deep dive.